Welcome to session 5 of Unit 6. Session 5 deals with the normal distribution, where normal distribution is quite voluminous. We're going to enjoy more slides in this one. That is another continuous distribution, that's a normal distribution. Well, in this section, you're able to list at least 3 characteristics of a normal distribution. Characteristics of a standard normal distribution, find the probabilities in the form P less P of z less small z for specified values of z. So let's look at some characteristics of a normal distribution. The normal distribution has a PDF of a continuous random variable x that has a normal distribution. Then it has a mean as a mu and the variance as a sigma square. So in this case, we use the random, or we use the notation. And what's the notation? That x is normally distributed as mu and variance square. Mu and variance square. Of course, if you check the function itself, it's quite some complex function. But don't be scared about that because it has been standardized. Nobody is going to ask you to use that function as the normal distribution to work anything. Nobody will ask you if you're checking your model. What other characteristics do you have for the normal distribution? Well, the graph of a normal probability function of any normal random variable, see, it's symmetric. What it means is that it's a bell shape and it's centered at the mean. So here you see that the mean is at the middle here, right? It's centered at the mean. Whilst you have a positive standard deviation here and a negative standard deviation. So we have about 3 standard deviation away from the left and 3 standard deviation away from the right. And one thing you also want to note is that since the normal curve is a graph of probability function for a continuous random variable x, now from the normal curve we talk about right now, we say that the total area under the normal curve, will be equal to 1 or is equal to 1. What it means is that where we have the mean being in the middle, half of the curve here, half here, will be 0.5. The other half of the left side also be 0.5. Now let's look at the standard normal distribution. So now everything has been standardized. A normal random variable denoted by z is said to have a standard normal distribution if it has a mean to be 0 and a variance to be 1. I hope it's clear. Standardized, it means that the mean is now being standardized to be 0 and the variance be equal to 1. So the whole of that complex formula will now reduce to this form. Very easy form, right? That f of z 0, 1 will be equal to 1 over the root of 2 pi multiplying e exponent minus z squared on 2, giving the interval minus infinity to positive infinity of z. Of course, once again, nobody will ask you to use this also formula because once it's standardized, it helps us, or it's been embedded in the table that will even help us to work out this easily. So don't be scared about the formula. Now, there are 2 questions that we need to seek answers to using the standard normal distribution. What are those questions? 1. Given a specific value of z, what's the probability that the random normal variable z assuming the value less than or equal to z? That is, what is the value of p assuming the probability of p as of z assuming small z? And also given a specified probability of alpha, what is the value of z for which this is equal to that alpha? Probability of z assuming small z is equal to alpha. Well, all those will be catered for in the lab. Maybe let's get straight to an example to help us understand the topic more clearer. Example 1. We have to find the probability of z less than minus 2.56 greater than 1.52. Z between minus 1.53 and 1.62. That is the problem. You go about it. Let's take the first part. One, this probability may be obtained using the symmetric property. Of course, P of z less than minus 2.56 is the same as P of z greater than 2.56. You know, symmetric property, what you have at the tail ends. The value here at negative side will be at the same value at the positive side at the tail end there. And how can this value be obtained? One, the only way we can do that is to use the standard normal table. So you see the complex formula we saw earlier having now standardized and made in a table form for us to read the values from the table instead of using the formula. So now what value are we going to read? We're going to read this value 2.56 from the normal table. And I guess by now we should be able to have a table and know how to read the table. Now how do we read a normal table? I'm going to take you through with this example. So we are going to read 2.56 from the table. For the normal standard normal table, the half table, we are going to read the first two digits. That is a 2.5 from the Z column, found on the Z column. On the Z column at the vertical section of the table. Then the last one, that's a 6, that will be 0.06 of the horizontal part of the table. So we find the intersection of them. So reading 2.5 and 0.06. Yes, in the column headed that. So this, from this, the formula will now be reduced to, because it's a half table and you are reading from the end of the tail end of the normal distribution, z greater than 2.56 will be equal to 0.5 minus p of 0 up to 2.5. Remember that, as I said, it's a bell shape. The total area under the normal curve, as I said earlier, is 1. So half of it will be 0.5. And this figure is read at the tail end. Let's look at the diagram here. So you see the diagram here. We are reading 2.5 and that's 0.06. That will give us 0.4948. That's the value. So this is a normal table when you get it. You see, that's we're going to have 0.5 minus 0.4948. So the value will now be 0.0052. So the probability in this form can be read off directly from the normal table. So simple. So we find the value, the original question that we have to find the probability of z less or equal to minus 2.56 will now be equal to 0.0052 as our ideal solution. The B part of the question, probability of z greater than 1.52. Also have that same format. So z greater than 1.52, that will be at the tail end. Look at the diagram. Yeah, this is a diagram. 1.52. So you are looking at the area, the shaded area here from the table. This graph shown here. So that's the tail end. You know that from 0 to where the z is all 0.5. So to get that shaded portion, that will give us 0.5 minus whatever you're going to read as 1.52. So from the normal table, you're going to read 1.5 and 0.02, just as we did earlier from the previous example. And that will give us 0.4357. And working out everything just as we did earlier, we now have 0.5 minus 0.4347, giving us 0.0643. 0.0643. 0.0643. As you can see from the shaded graph. Okay, let's continue with the C. C part is asking us to find the probability of Z between the intervals minus 1.53 and then 1.62. So this is a range. So as you can see from the graph, it's a range. So what it means is that the values that tends from minus 1.53 to this. So it means that from 0 to that minus 1.53 and then from 0 to 1.62 we're going to be added together. And finding that from the table, of course, we don't have a negative value on the table. So that value minus 1.53 will be read as 1.53. So we're going to read 1.5 under 3 under 0.03. And we're going to also read 1.6 under 0.02 from the table. And those values will give us 0.447 and 0.4370. Adding them together, as we indicated there, will give us 0.8844. Very quite simple when you have the range 1. Yeah, let's make a progress and look at a more complex example. And now come to the standardization theorem. So if x is normally a random variable with a mean mu and a variance sigma square, then a random variable z will now be standardized to x minus mu over sigma. This is what we call the standard normal. Standard normal. Standard normal. Maybe the example will tell us more. Let's give you an example. A weight reducing diet involving only liquid protein and bread is being advertised. The random variable x is the amount of weight loss at the end of the first week. Suppose x is normally distributed with the mean 12 and the variance 9. What is the probability that the person who is put on this diet will lose A, less than 8 kilograms in the first week, more than 16 kilograms in the first week, and between 7 and 15 kilograms in the first week? So looking at the example clearly, you see that the first part talks about the less than 8, greater than 16, and the third one is an interval. That's how we talk about the interval part. So now let's work with this example too. So the first part, so we are required to find probability of x less than 8. Because the question talk about what? Less than 8 kilograms. So x is less than 8. Remember, the mean given in the question was 12. The mean given was 12. And the variance was 9, but in the standard form, we used the standard deviation, that's the sigma. So the variance is 9, and the standard deviation will be 3, that is the square root of variance. That will give us standard deviation. The square root of 9 will give us 3. So coming probability of x less than 8 will give us p of x less than minus 12 over 3. That will give us less than 8 minus 12 over 3. And this gives us probability of z less than minus 1.33. As you could see, the indicated things from the table here or the graph there, I've introduced there. So ours is to solve z less than minus 1.33. Of course, you know how it is done. That will be 0.5 minus p of 0 less than z less than 1.33. 1.33 should be read from the graph. And how will you read that? That will be 1.3 under 0.03. And reading that from our standard normal table will give us 0.4082, resulting in our final answer as 0.0918. I hope you can do the B part. The B part will be greater than 16, following the same procedure. Or still have greater than 1.33. And 1.33 will have the same value. That will give us 0.0918. Why? Maybe the C part will be a little dicey for you since you're going to have different values. Now remember, the C part is an interval. So this is what we wish to find from the graphic we see. It's an interval from 7 to 15, where the mean is 12. So splitting them and working out just as we learned from the previous example, we're going to have this to be between, the Z to be between minus 1.67 and 1.00. Of course, we always want to keep the value to be two decimal place, since the reading is in two decimal place, so that we can read negative 1.6 under 7 under 0.07, and we're going to read 1.0 under 0.00. So all those will give us for the table the values like this: 0.4525 plus 0.3413, and that will give our final answer as 0.7938. 0.7938. That's quite lengthy. It's cut short. Maybe there are a lot of examples in the model that you could work out it. Why don't you give a try to them? And as we prepare to the last session of the Unit 6, also continuous distribution. Do you know what is it? Let's look forward to that.